All right, let's get started. Happy Tuesday. I hope everybody enjoyed the long weekend. And then just a couple of reminders. We're kind of barreling towards the end here. So we have our last lab this week. So it's going to be our aspirin synthesis. I totally forgot about checkout, but let's do checkout today just so we're don't have to worry about glassware. So we'll do aspirin synthesis, squeeze in some checkout today. And then, so right next week, I think we decided that we will combine lab sections for Tuesday, if that's okay. And then, so if you're a Thursday person that can't make it on Tuesday, then just talk with me. We can do a little mini poster presentation. Again, I'm just trying not to make it into like a torturous presentation for the whole class for whoever has to do that. But we can do a little makeup for whoever can't make it on Tuesday, and then we'll have our poster session, we'll call it. So it should be fun, and again, it's good practice. And my biggest suggestion is just to take that PowerPoint that's on Blackboard and then kind of just delete it, make your own. Or if you want to start off with a blank template, go 48 by 36 or 36 inches by 24. Right, make sure you have a huge one tile poster, then you can design it, and then you can print it in like a tile format. And so, yeah. The sooner the better. I mean, people historically have been sending to me them on like Tuesday morning, and we're like frantically posting. Like that's fine. Like Friday that would be ideal, or Monday, just to kind of give me a little bit of time. So yeah, I'll put that if you want my help, then let me know sooner rather than later. But we'll say like Friday or Monday, and you can just email me the file, and then I'll have it printed and ready for you. And then, yeah, if you can get them to me earlier, then I can obviously help you. And then let me know if you need feedback on your paper. I've been very slowly kind of giving them back. I have probably a few sitting around that like have not made it back. But just get feedback. Again, I apologize. This quarter's like gotten away from me. I still blame the lack of 2 weeks of spring break, I mean. That really kind of killed me. But let me know if you want feedback. I'm happy to make like time as well individually. I'll try to see who I miss, but I know some people like didn't turn in a paper either, so just or send me a new copy for updated feedback, and I'll try to get that ASAP. Any other questions about the poster? I mean, honestly, your papers look pretty good from what I've read. It's just a lot of people, I think I mentioned this last week, but people were just missing like the graphics, which basically you're missing the part that you need for the poster. So hopefully when you do the poster, that'll help you kind of fill in the paper, because you can totally have, graphics, data in your paper. And that's mainly what I want to see from people, of like either schemes, and that means like a reaction scheme, reactant product, what's going on, or other, pictures of molecules. And then any data. So if you have like good data, good charts, right, throw those on there. That's kind of what we're looking for. So data, charts, and it kind of depends, obviously, on everybody's topic. Some people are kind of more prime for schemes and pictures. And then some people, right, will probably be better off just showing like some data and charts from the paper. And again, you're just pulling these from your different sources, right? Hopefully you're not spending time generating stuff. Just pull in some good charts, some good reactions, just to help highlight your points there. All right, so let's dive into our chapter. I'll try to highlight what we'll test over. Otherwise, right, we're just trying to take it in. Lots of fun facts here. And so we're looking at alcohols, aldehydes, and ketones. And so again, this is a good kind of warm-up for OChem, just being able to identify our groups. So there's our alcohol group of OH. And then we have our aldehyde. So notice aldehyde is where we have, right, our two, an aldehyde can be abbreviated like so, where you have a hydrogen on one side, so that's an aldehyde. And that has some implications for reactivity versus our ketone as an acetone here. So the general form is that it has just kind of carbons or other things continuing. So right, carbon as opposed to the hydrogen there. So pretty subtle, but we'll look at those reaction differences. And so we'll also look at some naming. So kind of, again, I don't want to like over test us on this subject, but we still want to start being familiar. And so we have, let's start with methanol, right? So methane for one carbon. Here's two different representations of it. But we have methanol for, right, one carbon. And then ethanol, so there's two carbons and an OH group. So alcohol. And then looking at this one, so now we have two different isomers for our propane chain, right? So what is drawn here is 2-propanol, or you probably know this guy as isopropanol or isopropyl alcohol. So this is your rubbing alcohol. And so notice, right, we can look at our naming convention. So we have 1, 2, 3 carbon chain, and then, right, either way we go, if it's in the middle here, it's 1, 2, 1, 2. So same priority. So that's how we get the 2-propanol name here. Otherwise, again, iso from this little iso group. And then could y'all draw me 1-propanol then? So what does that look like? Take a moment for it, right? We have isopropanol. What would 1-propanol be? Good, so OH in the first carbon and a straight chain. And so I'll draw it. So 1, 2, 3, then OH, and then just double count 1, 2, 3. I'm just making sure I didn't throw in an extra carbon. And so again, once you move on to OChem, if you do move on to OChem, right, count and double count your carbons so that you have the correct number. Yeah. Sorry, I don't. Yeah, so that's what I mean of like 1, 2, 3, and then you make your arm into the OH. Does that make sense? Or were you, like I said, maybe I don't understand your question. Like, oh, like that? But then that would be, that looks like ethanol then, right? So you do have to do the little bend. Yeah, because otherwise then that starts looking. Yeah, unless, like I said, you did like 1, 2, and then, I don't know, C, H2OH. I don't know if that kind of makes sense. But yeah, generally this is kind of the better form. So every end you want to make sure is like clear and distinct. And that's why I'm always like, count your carbons and then count them again, because it's easy to like be off by a carbon. So let's look at some other isomers. So see if you can draw, what would 1-butanol be versus, can you guys guess what T-butanol looks like? Or tert-butanol? I'll write the IUPAC name, 2-methyl, 2-propanol. So practice those two isomers for a second. So then 1-butanol, right, you can puzzle it out. So but for 4 carbons. So 1, 2, 3, 4. And then our OH, let me just double count. 1, 2, 3, 4. I didn't do anything. So there's 1-butanol. And then for T-butanol, did we get this sort of shape here? So right, but still 4, so 1, 2, 3, 4. And then we could, verify that they're the same formula too, even. So right, 1, 2, 3 carbon, or 3 hydrogens, 5, 7, 9, 10. So C4H10O, and then same thing. So 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens plus 1, so still C4H10O there. And then with these, you guys are probably also at least semi-aware that people write these formulas in different ways, right? So you could maybe, it would be better to write it as C4H9OH to emphasize the alcohol group. But again, you'll see that there's not a lot of consistency in chemistry, and then you'll even get to kind of the next stage in OChem where you're like trying to puzzle out what's what, and it's all a puzzle based off of this formula and all sorts of things, but then you're not given hints over the groups. But that's kind of where we're going, or where y'all will be going if you take OChem. And so now let's look at, well, what if we have multiple alcohols? So now let's go naming with multiple alcohols. And so now let's look at this molecule. And so it takes a special name when there's 2 of them now. And so we have 2, and either way, right, 1, 2, 1, 2, the priority is the same. And so then what's our main carbon chains? How many carbons do we have? So 2, so then that'd be yeah, so ethane or ethanol, but then when we have 2 of them, we have this special, so this would be called 1,2 ethane diol. So when you have multiple alcohols, then they're called this diol group. And then this one, not to be even more confusing, has a common name of ethylene glycol. So you may know it as that as well. Like I said, right, there's usually an IUPAC name, and then there could be a common name, and this goes back to why we have the caste system, so that each chemical has a unique identifier, so that when you have all these 1,2-ethane diol or ethylene glycol, we can all make sure we're talking about the same chemical, right, across languages, so that's helpful too, since chemistry is obviously international. All right, so then let's try to name this guy. And so, right, we had diol for 2 alcohols, so diol. So see if you can guess what 3 alcohol groups would be called. Try to come up with the name. And so maybe you could guess this name. So right, we have propane again, so 1, 2, 3 carbons. And then we have our OHs on the 1, 2, 3 positions. And again, either way, right, you could do 1, 2, 3 priority, doesn't matter. So this proper name is 1, 2, 3 propane triol. So there's a tri, right, for 3 alcohol groups. And then, so now let's look at some other derivatives. So then we can, let's just start with cyclohexane. Let's remember this molecule. And again, keep in mind that cyclohexane is 3D. So I didn't bring my baby organic kit to start proving that to you. But it does have 3D characteristics, right? So it's not flat on the plane. So good to, again, keep reminding yourself of that. And so then we can have a derivative with an alcohol on it. So then this would be named cyclohexanol. So cyclohexane, cyclohexanol. And so now let's look at what about derivatives of it. So we have OH and a methyl group here. And so try to guess what the name of this would be. Again, right, I assign priorities. You have your cyclohexanol group here. You should give the OH the priority too. So any guesses on the name? Good. So I'll repeat it. So 2-methyl cyclohexanol. And right, it was 2 since, again, you want the numbers to be the highest priority. So of course you could go 1, 2, 3, 4, 5, 6, but right, that assigns it as a pretty low priority of 6. So it's much better to do 1, 2, so that your cyclohexanol is 1, and then 2. And then we only need to state it for our 2-methyl, given our relationship. I think that's kind of, there's like small discrepancies with that as well, because sometimes people put like dashes and stuff, but, or a space. Yeah, I think this one's supposed to be like one word, but like I said, you will probably see minor discrepancies and differences. All right, so let's look at our cis and trans isomers. And so these are kind of a little funny. Oops, so sorry, I forgot to put my alcohol on there. And so I'll give you the name for both of these once I. So 1, 2, 3, 4, 1, 2, 3, 4. Sorry, just making sure I have the right carbon count. And so now we have, again, our cis and trans alcohols. So this is our cis. And so then this would be called cis. And then 2 to indicate the position of the double bond. So cis, butene, and then 1 all to show the position of the alcohol. So this one is a little funny looking in naming. And then this would make this one trans to butene 1 all. Again, showing our position of our alcohol. And so then other ones that I feel like we've seen this one. Well, actually, we've probably seen it maybe in our weak acid page, if you remember. Not that I expect you to remember this one. So this is, you probably know it as phenol, or if you've seen it, it's phenol. It also has an alternative name, benzenol, right, for benzene, and then an alcohol. But again, these rings tend to take this name of phenyl then. So phenyl rings are the more common name for an aromatic alcohol. And then this is a weak acid. So I did want to kind of show you why these aromatics, how they function as an acid, right? And so just kind of thinking about why it's a stable acid. So again, this is kind of some OChem training, but also good, right, to kind of re-emphasize our acids and bases and, well, what does truly make something, right, a stable acid or stable base species. And okay, so it's acidic, and so if it's acidic, right, we can deprotonate it. And then that leaves us, well, first of all, with this structure, right, so our oxygen takes the negative charge from, right, the deprotonation. But then again, why this can function as a weak acid, and now this is kind of starting to just touch into a little bit of aromatic substitution. Well, we could draw a resonance structure. So then we can put our double bond here, and then we have, this would give us, well, we have 1, 2, 3, 4 bonds, right? So if I make a double bond, well, then now I have to do something with these electrons. And so then they can go to here. So I'll kind of redraw that, right? So then we've made this resonance structure where our negative charge is here. And then we can kind of continue to play with this, right? So then we could move it here, then move the negative charge over here. So I redraw that. So double bond, negative charge there, and then we can keep going. But all this is to say, well, our negative charge is then resonance stabilized, right? And so again, this is why phenol can actually be an acid, is because you deprotonate it, and then this negative species is stabilized by these resonance structures. So that is why it's an acid, right? Yeah, so these would be like the ketone forms. You could say that it undergoes like resonance structures that make it a ketone. Yeah. And so then we can have, let's do a few other naming. So then you can have these substituted phenyl rings, and then, oh, and so if we draw it here, you could maybe guess the name, or maybe guess one of the names. So any guesses? So 2-bromo, but then this isn't, yeah, good. So 2-bromophenol, good. And then, so we also have other notations that we could bring into play. So when you have, let's just say our alcohol, and then we're trying to describe positions in relation to this, we can also use the term ortho. So this is called ortho meta, which I think is abbreviated with an M. So we have the ortho meta and then para position, so P. And it would go on the same way, so ortho meta para. And so that is another way to name it and describe it. And so another name could be ortho-bromophenol. And so the 2 and the ortho are used, like I said, very interchangeably. So expect to see bottles with one or both of those names. So let's do some other kind of weird naming. So now what if we have our phenyl ring again? But what if instead we have a group here? Any guesses to its name? What's this group right here? Give y'all a hint. Yeah, methanol, right? So methanol, so then a name for it can be phenyl methanol. Or, again, not to confuse y'all, the common name for this substance is benzyl alcohol. So, and so let's try another one. So if this is phenylmethanol, then see if you can name, let's name both of these. So let me, one, two, three, four. So try that one versus try to name both of those. Any guesses for this one? This one could be kind of weird too. So phenylbutanol. I like it just properly. So the most proper name is that you want to name our phenyl group and our alcohol. So it's fine to give alcohol our first priority since we have our oxygen. So that's a higher molecular weight than carbon. So this takes priority. So then technically it should be 4-phenyl and then 1-butanol. Since, again, looking at your chain here, and then they're treating phenyl as just a substituent. And then what's the difference between this one and the bottom one? So what butanol is this? Good. So then this would be 4-phenyl properly, and then 2-butanol. Excellent. But it's off of the fourth carbon. Yeah, because it's treating it as a group that's hanging off of the fourth one. No, yeah, you just count like where it's hanging off of. Yeah. But like I said, I probably won't get like too tricky like this on your exam or anything, or I haven't quite decided how I'll test y'all. Or I mean, I have my old exam, but I was thinking about changing it up a little, maybe do matching or something. All right, so let's look at a few reactions. Again, just trying to introduce y'all to things. And so methanol can be reacted with sodium to produce this sodium methoxide. And so sodium methoxide is just a common base now, right? So you can see how that deprotonates the methanol. So this is just a base that's used in different organic reactions. So you'll see this a lot. Other reactions that they can undergo are these kind of acid catalyzed dehydration reactions. So dehydration, right? You're losing water. And so you can kind of see, we won't go into the mechanism, but at least you can lightly appreciate it. So if we're making a double bond across here, right, we're removing these the water that's across, right? So then this hydrogen goes or this OH goes away, then one of these hydrogens go away. And then you can see that they happen under pretty forcing conditions. So that's going to be, right, like acid catalyzed at 200 degrees Celsius. So like refluxing in acidic conditions. So pretty harsh. But you can take your alcohol and then turn it into a double bond here. And so let's compare. And so this is something that I might test you guys on. And so we want to take a look at the difference between our primary, our secondary, and then our tertiary alcohols. And so you can kind of see it hinted from this step. But starting off, so we'll learn that our primary alcohols, so they have, right, they have a bunch of H's attached to them with our primary alcohol. And so they can undergo 2 oxidation steps. So we'll look at those products. Now looking at our secondary alcohol, so our secondary alcohol, the difference is that it only has 1 hydrogen to lose here, right? And because we can only lose 1 hydrogen, we can only undergo 1 oxidation step. And then what distinguishes our tertiary, so looking at our tertiary alcohol, it's connected to no hydrogens, and so therefore it cannot undergo oxidation. So like I said, I'm not quite sure of what I will test you all fully, but I probably will have something about this. So I'll like star this for y'all. So I do want you to know the difference between our primary, secondary, and tertiary, and at least something about, again, that our primary undergoes 2 oxidation steps, and our secondary only 1, and our tertiary none. And so continuing that, so now we'll look at our aldehydes and ketones. And again, continue to look at our reactivity. And so then there's our oxidation reaction. So starting with 1-propanol. So again, our primary alcohol. And then this is our strong oxidant of our chromate. And then we make propanol. So we'll go over the naming, but this is for our aldehyde formation here. So notice like these ones, so going back to the naming, this is formaldehyde, but by the proper IUPAC naming, it's methanol. And that's really, I mean, I feel like it's really hard to tell, at least verbally, the difference. So methan, and I mean, I've never heard of anyone say methanol. It's always called formaldehyde, but like I said, this is the proper IUPAC naming. So same thing with this one. So now we have 1,2 carbon chain on our aldehyde. And so this would be ethanal, right, with a AL, but again, verbally very hard to distinguish, right, between our alcohols. So I pretty much have never heard anybody use this naming in practice, but again, there's a lot of inconsistencies in naming. And so this is mainly known by its common name, acetaldehyde. And so again, we'll continue on with our reactions in a second, but looking at propanol again, right, why it's going to undergo another one is that it has this H here, right? And so that's kind of the second note that we can add to it. So a primary alcohol goes on to make an aldehyde. Again, with that hydrogen hanging off of there. So it can go on again under another oxidation. And let's compare that for a second with our, so look at this one here, RR. So this is our secondary alcohol, where it's only attached to one other hydrogen. And so when it undergoes oxidation, then it's going to form our ketone. So our ketone again has no hydrogens, just some sort of carbon or other substituent there. And so it cannot undergo a second oxidation. So yeah, essentially, yeah. So that's one way to simplify the oxidation reduction. So yeah, we have to be able to remove a hydrogen to undergo that. And I don't know if we should kind of rewrite that. So I'll just kind of rewrite this while we're looking at our series that again are tertiary alcohol. And this little O can also mean oxidant. So you might see this O abbreviated. And so again, there's no hydrogen. So no oxidation. And so I'll just put an X there, or no reaction. So we're not going to see a reaction with our tertiary alcohol in any strong oxidant. All right, let's look at the formal naming. And so like we're kind of seeing, we take the name from the parent chain, and this time the ending is replaced with an "al" ending, which I think feels awkward. And then in this case, the aldehyde is usually given the number 1 priority, and therefore you don't include the number in the name. And then we also have, for common names, then sometimes you might add the aldehyde at the end. And so we'll look at those 2 different naming systems and then see how it changes when we have a carbaldehyde. So let's start with, I'll just rewrite out ethanol, right? So it has 2 carbons, and so that's why it's ethanol. Trying to emphasize the naming. And then, like we said, right, it has the common name of acetaldehyde for like the acetate structure. So acetaldehyde. And so let's look at another one. If I can count this, 1, 2, 3, 4, 5. So 1, 2, oops. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So this, we could either call it, so it's a 5-membered carbon, right? So 1, 2, 3, 4, 5. And so one name for it would be pentanol, or, not that I would expect y'all to know this, but this has a common name of valoraldehyde. So this must be known with the OH as, I'm not sure where they got the naming, but that's the common name for it. And then now let's try, where's my cheat sheet? This is what I was looking for. Oops. Let's copy this up here. And so let's look at some more fun. So what if we had 1, 2, 3, 4. Uh-oh. 1, 2, 3, 4, 5. Okay. What if we had this one, but now I'm going to stick a chloro on there. And we'll look at these positions. So can you come up with maybe one potential name for it? So 2-chloropentanol. Exactly. So that's one appropriate name. And so I threw this up here because, again, chemists can't just have one name for anything. And so sometimes these positions are known by their letters. So this is the alpha position, that's one away, the beta, the gamma, and delta. And so if you didn't like the 2 option, then you can also describe it with these alpha, beta, gammas. And so another alternate name, again, going off of the position that your chlorine is off of from here, could be alpha chloro oops, I dropped my N up there, pentanal. Or if you like this valoraldehyde, then you also have your permutations with that. So you could have 2-chloro valoraldehyde or alpha chloro valoraldehyde. And again, I think this just makes a great case for the caste system, since There are at least 4 proper names for this compound. Yeah, so you're saying, so if we had boom, 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 and then off of the same one? Yeah, so then in that case, right, that would be, so 2, 2, and then you could go bromo, chloro, and then whichever one you like, pentanal. Yeah. And then, so with that, let's practice another kind of alpha beta one. Oh my gosh. So 1, 2, 3, 4. So see if you can come up with a name for it. And so this could be, if you notice, it had a methyl off of the beta position. And so you could have gone, right, we could still do 1, 2, 3. And so it would be fine if you did 3 methyl butanol. So 1, 2, 3, 4. Or beta 3 should be, because it's 1, 2, 3. Yeah, and that's what's kind of confusing is like it starts, so you have your ketone and then the naming starts, or the alphabetical system starts after, so alpha, beta, gamma. But yeah, when we number it, we start with the number 1 being there, so that's kind of confusing. Yeah, so beta methyl butanol. And if I knew the common name, then we could use that, but I don't know them all. And so let's look at a carbaldehyde. So then we can have this cyclohexane group and then put our aldehyde on here. And so this is cyclohexane carbaldehyde. And just so you can see another permutation of this. So if we stick, let's say, a methyl group off of that, so then this is still kind of considered our carbaldehyde. So it should take first priority, then 1, 2, 3, right, as opposed to 1, 2, 3, 4, 5. So then this will be 3 methyl cyclohexane carbaldehyde. All right, that's a good spot to take a 10-minute break here. So yeah, let's take a little break and then we'll be back with more naming fun. All right. Any questions come up as we come back from break? Again, not the most like thrilling topic, but it's still good to lay down these foundations so that when you go to OChem, you're not like completely clueless. But like I said, we'll keep the testing itself light. Not trying to drive anyone away at the last minute. We're here at the home stretch. All right, so now ketones are pretty similar. And so now we have this own ending. And then again, same thing. We'll list alphabetically and then add our ketone. And then we'll, of course, look at a few scenarios. So here's our aldehydes again, just kind of reminding us. And then our ketones. And so we'll go over kind of the two different ways to name them. And so if you look at it, so we have our two proper IUPAC names. And so we can either name it as the full chain. So if you look at this one, and so right, a ketone will have obviously carbons on each side. And so this is 1, 2, 3, 4. So your whole chain. So that gives you butanone. Or the other naming system is, okay, well, you have half of this is an ethyl group, half of this is a methyl, and so then you can name it by methyl ethyl ketone. So by your two little halves there. So same thing with this one. So again, we have 1, 2, 3, 4, 5. And so we have 2 pentanone. So in that case, they did specify where the ketone is, right? So 1, 2, 3, 4, 5. So 2 priority. Or the other naming, again, so this side is 1, 2, 3. So that's propyl. And then a methyl. So that's how we get methylpropyl. Again, just alphabetical order. Although there, they didn't do that. But methylpropyl ketone there. And then, so this one we can compare to the 2. So now it's in the middle. So 1, 2, 3. And if we went 1, 2, 3, right, same numbering. So 3. So 3 pentanone, or, right, we have 2 ethyl groups. So that's where we get this diethyl ketone. And then this one down here, so they don't have another name for it, but instead just name it by the 2 halves. And so now we have to, or actually no, sorry, they name it, they didn't give the other name, because I was going to say what that's like, isopropyl methyl ketone, or they just did it 1, 2, 3, 4. So 2 is your butane, your ketone priority. 3 is a methyl, so this should have higher priority. So that's how they got 3-methyl-2-butanone. But I still think we could call it so. Iso. All right. Let's see what other naming things. Yeah. Sorry. Isopropyl methyl ketone would be the other name that they didn't put. So let's try one more. So if I draw you this one, 1, 2, 3, 4, 5, 6. All right, so give me either one out of two names for that. Yeah, so I feel like that's my favorite way to name it is by the two groups. So ethyl propyl ketone is one IUPAC name, or if you wanted to list the whole thing, so we have a 1, 2, 3, 4, 5, 6 carbon chain, and then 3 is a priority, right? 1, 2, 3. Otherwise, it's 1, 2, 3, 4. So that doesn't make sense. So 3 hexanone would be the other name. And so now let's look at this funny one here. If I can draw it. 1, 2, 1, 2, 3, 4. Okay, this is a weird one. So let's kind of point out what we have, right? So we have our aldehyde here. And then, so let's count. So this should get priority. So 1, 2, 3, 4, 5. And then these are basically our oxo groups again. So if you remember those naming. And so then we could name this one. So then, right, it's 3, 4. So then 3, 4 dioxo pentanal. So that would be our proper naming there. And so let's look at what if we don't have an aldehyde. So now let's look at this scenario. So 1, 2, 3, 4, 5. So now we have just ketones here. And so the proper IUPAC name for this molecule is 2, 4, right? So 1, 2, 3, 4, 5. So that gives us 2, 4 pentane dione. So there's a di that there's, right, 2 ketone groups, dione. And so let's look at just some other permutations. So now this is cyclopentane or cyclopentanone here for, again, ketone. And then, so same sorts of things. So let's look at some other combinations. So we could have cyclohexane. So let's look at these two. So see if you can come up with a name maybe for this one. And then we'll compare it to this one right here. Oops, forgot to take off my break time. So I'll give you these names. So this one is 4-bromo cyclohexanone. So maybe you could have guessed this one. And then this one is pretty similar, except right, you want to do that dione thing. So now it'd be 1,4-cyclohexane dione for our two ketone groups there. And so now let's just compare. What if we had an alcohol group in there? Or we could also call it another name. All right. So now we just want to go over how to treat our priorities. So the ketone or aldehyde should take the priority in this case. So this gets the 1, 2, 3, 4. And then, right, it's an aldehyde for the H there. And so the proper name for this would be 4-hydroxy. Remember, hydroxy is just another name for our alcohol. And then butanal there. Remember that Al ending for our aldehyde. All right, good. And then again, just another reminder that our tertiary alcohols, right, do not undergo oxidation. So let's try, see if you can name these last two ones here. So what if I draw some more practice? So try to name this one, and then we'll try another alcohol derivative. Or not alcohol. Well, yes, alcohol. Okay. So try to name those two. So let's see what you got for the naming. So what do we think? Let's start with this one. So 2-bromo. And then it's not a pentanol though, because what is this though? So it should be yeah, cyclopentanone there. Good. Excellent job though. And then what about this one here? So 4-hydroxy, and then what was your methyl? Yeah, 3-methyl. Yeah, butanol. Perfect. And make sure it's NaL. Again, it's really hard to tell orally. Good. I mean, honestly, y'all are doing really good with the naming since, like I said, we're just trying to peek into OChem so that we're not completely lost. Or if you don't go on to OChem, at least, like, again, you'll have some sort of background and knowledge. All right, so let's see how far we get on our carboxylic acid formation now. And so we'll look at our naming, but we can start to get a peek. So we have now this noic ending. So methane, looking at our simplest form. And well, let's take a reminder, right? Our carboxylic acid, we've looked at them in our acid-base chapter, kind of second quarter. Let's again remind ourselves, like, why is it an acid? So again, this is probably a refresher, but you can't see this enough. So, right, you've deprotonated it, you've made this form, right? So now this is our deprotonated. And again, why it's an acid is because this is stabilized, right? So we've drawn this before, but now we can take our resonance, so we can make our double bond here, kick this up, and again, right, we're just showing that we can stabilize this negative charge all along here. So that is, yes, why it is a stable acid. So that's our carboxylic acid group. And so we've seen this in, like I said, many organic complexes. So we've seen it with acetic acid shown here. So we're used to the common name of acetic acid, but otherwise, right, 2 carbons makes it ethanoic acid. So our carboxylic acids again have the double bond and the OH now together. So you'll be, like I said, ready for OChem, so you're not completely clueless on these groups. And so now we're continuing on to from our alcohols, right? So we said our primary alcohol made an aldehyde, and so we could say, right, this was maybe from a primary alcohol. So we could oxidize it. Now we're at the aldehyde. And then, like we were hinting at, well, we can continue now with an oxidizing agent to make our carboxylic acid. And so here are just some examples. And so I will do, like I said, I promised y'all the silver test last week, and then I didn't do it. But I will do the silver test this week because it is kind of more appropriate for this chapter. So I'll do the Tollens reaction. And I'm just trying to think if I want to go into any other oxidizing agents, but I think it's fine. And so, again, we have kind of our common oxidizing agents. I'll just abbreviate it. But we have our permanganate, right? That's an oxidizing agent, our chromate. And then you'll see other ones in OChem, but like I said, I didn't want to totally get into that. And so the main piece being that we lose this hydrogen and then it gets replaced by the alcohol group. And so we can see that again from our methanol, and then going to methanoic acid or formic acid or ethanol, going to ethanoic acid there. So as long as it has an H attached to it, right, it can do the reaction. So that's again our kind of key piece there. And so this is, again, just recapping that we could do this, right, a two-step reaction. So again, we do one oxidation to make our aldehyde from our primary alcohol, then do a second oxidation to make our carboxylic acid there. And then just again another reminder of why this is an acid from our resonance stabilized carboxylate ion, like we've seen in acetate and acetic acid. I'm like flying through this chapter. All right, so let's start going over the IUPAC naming for our carboxylic acid. And so like we're kind of seeing, we changed the ending to anoic acid. And in this case, right, your carboxylic acid will always be at the end. So it is given the number one priority. And so you don't generally put it in the name. And so all these are good examples. So we can start off with propanoic acid. So 1, 2, 3. So propane, right, our 3 carbons, and then noic acid for our ending. And then so now we have 1, 2, 3. Once again, so there's our propane. And then 1, 2, 3 for our priorities. So then we get 2 chloro there, so 2-chloropropanoic acid. And so now same thing. So find our longest chain, 1, 2, 3, 4, or 1, 2, 3, 4, it doesn't matter. We still get that it's off of our 3 position, so 3-methyl butanoic acid. And then this one's a good one. So this one, right, we have 1, 2, 3 carbons. So there's our propane. And then we have 1, 2, 3 chlorines. And then you put them in every position. So there's 2 chlorines on the 2. So 2, 2. And then 1 on the 3. So 2, 2, 3 trichloropropanoic acid there. And then when you have carboxylic acids with an alkene, then we want to put the location of the alkene, longest chain, and then our appropriate ending there. So now looking at these, right, we have our, so now they're on opposite ends, so that gives us the trans conformation. And then 1, 2, let's write it 1, 2, 3, right? So 3 tells us the beginning position of our double bond. And so that's how they get trans 3-pentenoic acid. And that's kind of confusing. So look, the pentene, right, for your alkene, and then pentenoic acid. And then, so same thing, let's look at this one. So 1, 2, 3, 4. So there's our butene, right? But butanoic acid. Now your two main groups are on the same side. So that's how we get E there, or cis, right? So we could have also called this cis. And again, so 2, so cis 2, methyl, then 1, 2 for where your double bond starts. So 2 butenoic acid. And so let's look at a few other naming examples. So let's start with, so let's make our so now this would be, you could probably guess this one. So cyclopentane carboxylic acid. And so now let's try, I'll let you try this one. And now I'm drawing stereochemistry on purpose. So try to give a stab at the naming, so think about it for a little bit. Oops, go away. So then I drew this one pretty particularly, right? So I was showing these, so they're on the same side. So this would be cis, and then remember this is always given the 1 priority. So this has to be 2. So cis 2 bromo, and then cyclohexane. Oops, sorry, I misspelled cyclohexane. Cyclohexane carboxylic acid. Yeah, since we're showing stereochemistry, so that'd be the proper name that you're trying to show that they're both flipped up on the same side. Again, I should have brought a kit. And then we can compare this one then. So kind of to your point and to your question, the distinction would be, what if we had this group? So now you can probably guess the name. And so now, right, they're kind of opposite sides, so one up, one down. So this would be our trans isomer. So then this is trans 2-bromo cyclohexane carboxylic acid. Yeah. Well, yeah, that's what's giving it, like, that's why they also name it as carboxylic acid, because this should have the priority. And then, yeah, this has to go off of the one carbon then. But yeah, it's kind of because it's like not really in the chain as much, so that's why you switch to this carboxylic acid versus like the butanoic acid where it's like more incorporated. But that being said, there's probably alternative names. And so let's look at some more common names versus IUPAC. So see if you can guess this one's name. So any guesses for this one? So what's so it's not a phenyl though, right? Because we don't have a, but we can still just call it benzene carboxylic acid though. Uh, Phenyl usually has the OH on it. Yeah, like phenol. And then the other name that this also has is benzoic acid. So this is the more common name. And, well, let's try this one since you guys like the phenyl rings here. Let's give you a phenyl ring. So any guesses for this one's name? Oh, yeah, you should name it for the 2, for the fennel. Yeah, so 2. So you can call it 2-phenolic acid. So that's one of the names for it, for our phenyl group. And then, right, implying that it's a carboxylic acid group. Otherwise, the proper kind of name would be 2-hydroxy benzene carboxylic acid. Or, for some reason, this one has a common name, and you may recognize it. I don't know if you guys have read your lab, but this is salicylic acid. And so this is our precursor. So we're going to be starting with salicylic acid to make aspirin today. So a bunch of different names. And so let's try some more permutations, combinations of names here. So what if I give you this one? So how do we name this one? Any guesses for this one? Good. So 3-hydroxy pentanoic acid there. So let's look at those oxo groups again and see if we can name them. So now we have a carboxylic acid, and then, sorry, one. And so we can still treat this as an oxo. And remember, our carboxylic acid is kind of dominating the naming. So take a stab at naming it. Any guesses for this one? It should be 4. 1, 2, 3, 4, and that's supposed to be a H. And then if we look at the oxo group here, so it's 1, 2, 3, 4. So we can name it 4-oxo, and then for those 4 carbons, butanoic acid. And then let's just practice another one that's kind of similar. It's another oxo group there. Any guesses for this one? Perfect. 2-oxo-pentanoic acid. Again, you guys are impressing me with your naming skills. All right, let's try. So we haven't practiced some of our other groups in a minute, so let's look at those. So we see a lot of amines in OChem. So there's a simple amine there. So looking at this one, we'll break it down. So 1, 2, 3. So just a 3-chain. We have our amine hanging off of the 3 carbon. So 3 amino and then propanoic acid. Let's try. We haven't seen, what if we have 2 carboxylic acid groups? So let's look at that and how we would name it. So now 2 carboxylic acid groups. 1, 2, 3. So right, 3 carbon chains. So propane. Now we have 2, so dioic acid. So there's that dioic there. And then this one, right, they should be at the end, right? So your carboxylic acid should always be at the ends. And so that's why we don't need to put the positions, right, because they're flanking the end. So same thing, so we could do something similar. if I can draw it without screwing myself up. So 1, 2, 3, 4. Oh. So 1, 2, 3, 4. Oops, and I forgot that should be an OH. There we go. And so this would be, again, similar to this one. Your carboxylic acids are flanking the N. So we can name this one for our 1, 2, 3, 4 carbons. So that's butane dioic acid there. All right, that's probably a good place to stop for the day. So we'll pick back up on Thursday. We'll keep kind of doing some naming practice. And you can always feel free to give me opinions too on how I should test y'all. I try to keep it light, like I said, but we at least want to have some background, right? So again, we're basically at the end here. So next week, right, we'll do a little bit of like polymers and kind of touch on biochem. But we're basically just kind of at our end chapters, right? Just trying to tie up the loose ends, get us ready to see new things and higher orders of chemistry. All right, make sure you grab the homework in the lab, and then lab should be fun. So we're doing real synthesis, starting with our salicylic acid here, or 2-phenolic or 2-hydroxybenzene carboxylic acid, and we'll make our aspirin. All right, I'll keep the stream running for another minute or so in case there are questions. Otherwise, I'll see y'all in lab today. And like I said, just let me know if you can't make it for the poster session next Tuesday so we can figure out an alternative arrangement for you. And then let me know if you need help with the poster.